In this lecture, we're going to take the definition of the limit of a sequence that we talked about in the last lecture and see how we can apply it to find the limit of some specific sequences. So first, just be aware that we're talking about the limit of a sequence here, not the limit of a function, since we're talking about a function of n rather than x. As we discussed in the first lecture, that's going to be our assumption throughout this whole series of lectures. So with that said, to show that 0 is the limit here, we need to start by picking an arbitrary epsilon greater than 0 and show that there exists an integer n. Show that it's a symbol for there exists, kind of backwards e. There exists an integer n such that for every n greater than that number, and that's a symbol for each or for all n greater than that number, the absolute value of a sub n minus 0 is less than epsilon. All right, well, on the left-hand side, let me write this over again down here. A sub n minus 0 is less than epsilon. Okay, so on the left-hand side, a sub n is just 1 over n. So this is the absolute value of 1 over n minus 0 is less than epsilon. Well, obviously, right, this is just the absolute value of 1 minus n. And this is just 1 over n because our n's, that's the index of our sequence. So those n's are all positive. Okay, but this is the same as n is greater than 1 over epsilon, which is what we needed to see. Right? What this shows that for every epsilon greater than 0, if we choose capital N equal to 1 over epsilon, then the absolute value of a sub n minus our limit 0 will be less than epsilon for every n greater than that number. So just to see this in action, right? Let's say we pick a specific value for epsilon. Let's say we pick epsilon equal to 0.1. Right, so our calculations here say that for every n greater than 1 over epsilon, right, which is 1 over 0.1, which is 10, the absolute value of a sub n minus 0 is going to be less than epsilon. Right, and we can see this, right? If you say let's pick a specific value just to confirm that it is. If we let n equal 11, then a sub n is 1 over 11, which is 0.9, and 0.09, which is less than 0.1. It is less than our epsilon. Now, this one is pretty straightforward, but it's going to be useful later on, so it's worth talking through. In fact, this would be a good example for you to pause the lecture and try working out yourself before listening to my argument here. Okay, so a sub n is k for every n. It's a constant sequence. Well, this means that the absolute value of a sub n minus k is just the absolute value of k minus k, which is 0. And remember, since epsilon has to be strictly greater than 0, this is going to be less than epsilon for every n. And that's what we needed, right? For every epsilon greater than 0, the absolute value of a sub n minus k is less than epsilon for every n. Good. That's what we needed to show that this is the limit here. All right, so we actually talked about this sequence briefly in the last lecture, but it's a good example to illustrate how the definition of a limit that equals infinity is going to work. So let's walk through this. We're going to start by picking an integer m, that m be an integer and m is greater than 0, then what we need to do is we need to find another integer, capital N, such that a sub n is greater than m for every n greater than that number. All right, so to do this, suppose we let n equal n plus 1. Right, then look at what happens. Right, if this is the case, then for every n greater than n, we have the absolute value of a sub n equals lowercase n, which is greater than positive n, right? Because that was our assumption here. But positive n is m plus 1, which is greater than m. Right? So if we cut out all the middle stuff here, for every n greater than this value, the absolute value of a sub n is greater than m. And that's what we need to show that the limit is equal to infinity. In all of the examples so far, the limit has existed, even if the sequence diverged and the limit ended up being infinity. Now, in this example, you can see a sequence where the limit simply does not exist. Right? You can see what the sequence looks like in the graph over here to the right. This is the simplest example of an oscillating sequence, one that bounces back and forth between positive and negative values. Right? So to see why this limit doesn't exist, start by letting L be a positive number and let epsilon equal 1/2. Now remember that to show something doesn't exist, we only need to show a single counterexample. In this case, that means showing that there exists at least one value of epsilon where we can't find the value of capital N that the limit definition says we have to have. Right, so for this value of epsilon, if we choose any value of capital N, right, so let n be an integer where n is greater than 0, okay, and let lowercase n be an odd number greater than, whoops, can't spell today, greater than n. Right? In this case, what happens? Right? The absolute value of a sub n minus L is equal to the absolute value of -1 minus L. A sub n is -1 here because n is odd, right? And the odd values, the odd indexes are all these negative values down here, right? So this is equal to the absolute value of 1 plus L. And because L is a positive number, L is greater than 0, this is greater than 1/2, which was our chosen value of epsilon. Right? So what that means is that L can't be the limit, right? Because there exists an epsilon for which we cannot find the required value of capital N, such that every value of the sequence greater than that number is within epsilon of our hypothetical limit. Right, now, so far we've just shown that there's no positive value that's equal to the limit of the sequence, and showing that there isn't a negative value follows a very similar pattern, right? So I'm going to leave that as an exercise. In the next lecture, we're going to revisit some of the rules that we had for working with the limits of functions, show that they work just as well for the limits of sequences, and then we'll see how we can combine those rules with just the handful of limits that we derived here to find the limits of a bunch of other sequences.